A very good evening to everyone. The topic of today's presentation is modeling and optimization of 2D volumetric sound diffusers. Hello everyone, my name is Rohit Dantkale, a mechanical engineering student at San Jose State University. My passion is to work in autonomous vehicle industry. Currently I am doing research under Professor Bares to design a solid structure of safety guidelines for autonomous vehicle of level 5. Thank you.
Hello everyone, I'm Bhartwaj Jagannath, a mechanical graduate student at San Jose State University, and I'm from India. Designing and fabricating RC planes and drone piloting is my passion, and I've almost designed about 10 to 15 RC planes and flew about 10 to 15 of them. In 2019, was the team lead for the micro team at SAE Aero Design West, which was held in Los Angeles, where I loved designing the micro model, which has to fit in a box which is as small as the cake box.
Hello everyone, my name is Harshit Shah. I am from India. I am currently in my last semester of my master's program and I am passionate about cars and its technology because I did my bachelor's in automobile engineering and I also work with cars for 3 years.
These are the contents for the presentation: objective, motivation, background, methodology, design, result. The objective of this project is to maximize the diffusion coefficient of a uniform configuration of scatterers. This would be done by modeling and analyzing multiple scatterers for two diffusers using MATLAB FMINCON solvers. Many different configurations would be used for rigid cylinders and elastic shells in air medium. Here is a brief background on diffusers. Diffusers are the material used to treat sound aberrations such as echoes in the room. They are used to effectively reduce distinct echoes and reflections while still living in a live sounding space. Diffusers are installed in spaces such as auditoriums, concert halls, classrooms, and recording studios. Unlike reflective surface, diffusers scatters the sound in all different directions to maximize the diffusion coefficient. Diffusers are generally placed in the center of room to get maximum sound wave diffusion. They are mainly divided into two categories that are one-dimensional and two-dimensional. There are many different shapes of diffusers, but among which are mentioned in the slide. But among all, cylindrical arrangements is the best as it scatters sound waves in different direction to get maximum diffusion.
For this study, analytical model is used to calculate the diffusion coefficient by means of multiple scattering theories. Multiple scattering is the acoustic time harmonic wave equation is in two dimensions. K is the wave number, P is a total pressure field, P is a incident pressure field, and P underscore SC is the scatter pressure field. The incident field is a plane wave which interact with a given configuration of m separate scatters. Circular cylindrical scatters could be either rigid or thin shells. The application of the boundary conditions at the interface between each scattered and excited medium yields equation as shown below. Formulation to calculate the diffusion coefficient is shown below. A cylindrical configuration with a diffusion coefficient of 1 would have a perfect diffusing configuration. Cylindrical configuration with a diffusion coefficient of 0 would have a specular diffusing surface. PSI is the angle of incident, Li are a set of sound pressure level in decibels, N is the number of receivers in the polar responses. The goal is to increase the scattering and thereby the diffusion coefficient by rearranging the scatterers. This is the 2D volumetric sound diffuser design. The objective of this study is to model and analyze diffusion of 2D MetaDiffusers that consist of a uniform configuration of cylinders and optimize their position to produce a maximum diffusion. To do this, MATLAB FMINCON solver is used. The frequency range used for this study is 0 Hz to 20,000 Hz, which is the human audible range. fmincon is nothing but a gradient-based solver that is designed to work on problems where the objective and constraint function are both continuous and have continuous first derivatives. All these algorithms have ability to input user-evaluated gradient. All this study depends on the fmincon solver to estimate gradient of the nonlinear constraint using finite differences. Algorithm that is used is sequential quadratic programming, it's SQP, and some different algorithms have also been used for comparison such as ActiveSet, interior point, SQP legacy, and these algorithms are used for simulation of single frequency optimization, broadband range optimization, and multi-start. Broadband optimization will optimize the root mean square of diffusion coefficient of broad ranges and frequencies. And multi-start is a global optimization toolbox on MATLAB. The solver only optimizes by taking a single random point inside the bounds, hence very likely to get stuck in local optima values. In multi-start, you can enter a number of starting point to increase the chances of finding global optima.
There are two cylinders used in single frequency optimization. One for rigid cylinder and another for thin shells. In rigid cylinder, we do not consider mechanical properties. Other than that, both have similar boundary condition. Firstly, we'll consider some random initial configuration with the number of points we need. Then the size of the cylinder, distance between the cylinder and boundary within the which the cylinder should be located is provided by us. Then the script then randomly generates a cylindrical configuration. In this configuration, the cylinder should not overlap and should be within the circular region. Then the script calls out for after that script calls out for algorithm. In addition to that, maximum function evaluation, maximum iteration, and step size are provided. Then fmincon computes the script and gives us the optimized diffusion coefficient. Using this, we compute for different number of cylinders and different wave number. This first diagram is a random cylindrical configuration within a circular region where the cylinders are not overlapping, and the second diagram is for the second graph is for the pressure field, which is for the before the optimization. Then the third graph is for the optimized pressurized field. In this has the we have computed for the different number of cylinders and different number of wave numbers. As the number of cylinder increases, the optimization gets better, but as the wave number increases, the optimization gets intensive. So we need more resources for the optimization for the higher wave number and high number of cylinders. Then in this, we are using different algorithm, which are interior point, SQP, and SQP legacy, ActiveSet. In this, we have computed for the wave cylinder number of 15 number of cylinders and the wave number of 150. The SQP and SQP legacy takes more time than SQP, whereas ActiveSet takes lesser time than compared to the both, and interior point takes utilize a lot of time in computing. So in most of the computing, we have utilized SQP for our optimization. Then we'll move on to the next topic about shells. In thin shells, we consider mechanical properties, so the computation may be difficult. We are computing for the first the images represent for the 20 cylinders and wave number 100. The first image shows a random cylindrical configuration. Then the second graph shows the initial pressure field before the optimization. Then the second image shows the optimized pressure field. Here we have computed for the different number of cylinders and different number of wave number. It is similar to the rigid cylinder. The number has the number of cylinder goes on increasing. The optimization gets better. But the higher the wave number increases, the optimization gets more complicated and requires more resources and time. From here on, Bharatwaj takes over.
Configuration of 10 and 15 scatterers were simulated with broadband frequency optimization. The minimum frequency was 2.74 kHz, the maximum frequency was of 5.49 kHz. This optimization was done using SQP algorithm. The number of frequency which we used was 3 here. As you can see, the final pressure field is not different from the initial pressure field. This is because the diffusion coefficient for the initial random scatterer configuration was about 0.31, and for the final diffusivity coefficient is 0.5888. So there is no much of difference here. This is because of the computing strength which we had in our computers. The rigid configuration of 10 and 15 scatterers was simulated using multi-start single frequency optimization. And the frequency which we used here is 2.74 kHz, and the algorithm is again SQP algorithm. As we can see, the algorithm is more accurate to find the coefficient of diffusion as close to 1, that is about 0.97355. And as you can see, the final pressure field is better when compared to the initial pressure field. In this study, it was demonstrated an effective implementation of multiple scattering for two-dimensional volumetric MetaDiffusor for 360-degree circular space. The study was able to simulate different sizes of configuration at higher frequencies and was able to optimize at near perfect diffusion, which other diffusers cannot. Only cylindrical diffusers can. It was also demonstrated that as the configuration size increases and frequency increases, the diffusion is very good, and the optimization time is longer. In addition to that, different algorithms were implemented, and the result shows that SQP algorithm and active set are the best working algorithms. The future work could be to extend the same codes for three-dimensional case such as spherical sphere, and the evaluation of gradients which is inputted by the user, so that the computational time of the solver could be reduced. So using COE HPCA clusters, we can optimize the large number of cylinders and then higher frequency models faster and efficiently. Fabrication of optimized cylinder configuration for physical testing in sound room. So we'll be testing the same configuration physically, and the simulation what we are performing here is a plane wave, and we can extend it to the source